Welcome back, Organic Chemistry. Let's take a look at our spectroscopy again. I love it. Okay, we ended with what a basic idea of what IR spectroscopy would look like. And now let's take a little bit to actually talk about how that works and how we can read that. So when we're looking at an actual covalent bond, and let's take a sample of something like acetone. Each type of bond, so I'm going to go ahead and include our hydrogens. Each type of bond will absorb in a different range. So all of these bond types are going to look different on your IR spectra. I love it. That is awesome. If you can connect where we absorb to a functional group, done, you're in business. You can take a formula like C3H6O and you can tell the structure. It's amazing. So how do we read this again? If I've got a nice sample of acetone and I am passing light through that acetone, and then seeing what pops out the other side, let's read the other side. So we start down at that 4,000 range, and we notice on acetone that all that light is coming through. We are at 100% transmittance here. And then we notice, this little haystack around 3,000. In fact, that drawing is just slightly misleading. We want our 3,000 up here, okay? So around 2,900 or so. We've got this little haystack, and then we keep going. And then we notice this deep peak right around our about 1,760. And then we start seeing some peaks in here. And maybe it gets just a little bit sassy down here in this range after that. And you're wondering, okay, wait a second. Okay, the shoe just dropped. Cliffhanger number 1. Why aren't there 3 peaks? There are more than 3 peaks. And why does it get complicated down here? All right, so let's add one little tidbit to our IR. And that is that what is actually happening to your bond and why can we see it? So if we take that acetone bond and let's look at just a basic carbon-hydrogen bond, these electrons are in motion. The actual bond is in motion. In fact, those vibrational modes and rotational modes and motions and bonds, there are up to 27 different motions and bonds and modes. We'll call them modes, vibrational and rotational modes and bonds. There's not just one. So what happens is you absorb a specific energy, and maybe you go from, that just doesn't look right, does it? And maybe you go from a motion like this, where you're stretching that bond, you absorb light, and now you stretch even faster. So now you're just cranking and you're stretching really fast, and then you emit that light and you go back to normal stretching. So you're not breaking the bond, you're not damaging the bond, you're just enhancing that motion. That motion is now, you take it up a notch, and then you go back down a notch. But because there's so many motions, that each one of these peaks is a bond type, this is our CH, but it will also have a specific motion. So, and same thing here. This will be specific to our C double bond O, but one particular motion. So that means when we get down here, we're going to see CH again with a different motion. We might see that CC here with a different motion. So our IR is always a little bit more complicated than just your functional groups because each one of those bonds has different motions. But the good news is that if you start here, you can typically read your IR and get to your functional group by here. Now, old school organic chemists, when they had only IR to work with, they got phenomenally good at this fingerprint region. And it's called the fingerprint region because no compounds have the same IR. So if you've got methanol and ethanol, they might be similar, but no two compounds have the same IR. They are unique. They might be similar, but they will have unique features. And say to each structure. So some of those motions we see very well in IR. Some of those motions you don't see at all. So for my MCAT people, a nice trick question, if those motions are symmetrical, you don't see them. You only see the asymmetrical motions, but we'll hit that in OChem 2. Our job in OChem 1 is to just learn how to read them and solve some puzzles with them. So my super secret is you start here and you end here. And 99% of the time you have your answer. And if you don't have your answer, honestly, you use another instrument. All right, so let's make this practical. Let me show you what an IR looks like. Now I'm gonna take something that is actually nice and straightforward, butanone. Look, I even gave us the answer. This is what the IR spectrum looks like for butanone. And now as a practical example, what would we do? We would see this formula in a roadmap. And we would be able to draw all of the functional groups that contain an oxygen and contain that formula. What IR lets us do, so that right there would give us several structures. Now what an IR lets us do is get to this structure by reading our functional groups. I'm going to start here. And I'm going to read this way, okay? I'm seeing nothing. These little guys, ignore. We're looking for the big ones, all right? The big ones are usually the ones that give you your answer pretty quickly. And I'm going to draw a little line right here. And I'm going to notice that these are on this side of 3,000. Your carbon-hydrogen bonds will always be right here. And we have several here, here, and here. That's why it looks like a haystack. Our whole class is organic, so we will always see these. Now we're going to be able to tell functional group, however, on what side of the 3,000 our peak starts. Now how do I know that? I'm going to scroll down. This is where we're going to use a table. Now I've given you a huge table. I've got 3 examples. There's a nice small one from Mastering Organic Chemistry, and this might be something that you want to write on your cheat sheet, but I'm also going to help you with that in class. All right, look at our CH stretch. That's right here. It's connecting to where you're going to read that in your spectrum. If our peaks start on this side of 3,000, we have a double bond or a triple bond, or a benzene. If they start on this side of 3,000, we have single bonds. So we need to take the bond type and correlate it to what we see in our spectrum. Now, why this document is so huge, this is from Sigma Aldrich, and this is a big one. So this is the end-all be-all, but the reason I like it is that it starts with frequency. Okay, we didn't see anything, nothing, until we hit down here, and that was in this range. And that is telling us, there's our alkane, and that is telling us, see, we went down about half the way in our spectrum, that's medium, It's giving us our bond type. It's telling us it's a stretching motion, and it's connecting to our functional group. So this can be a little bit intimidating, which is why we probably want to get to something like this, but I wanted you to have the resources in both ways. So our job in IR is to take IR and connect to our functional groups. So our CH, if I were you, I would put this in your own list with functional groups. We're going to do this in class, but you can certainly start it without me. Okay, now look, I don't see anything here. Nothing until this one. And where does this hit? This is about 1750, right? So if I look on my little indicator here, okay, ooh, look at right here. I didn't see anything in this range, nothing, but we did in this range. Look at that nice big peak. That is our C double bond O. So in our right here is this. So look at our compound. We just hit our two functional groups right there, CH bonds and C double bond oxygen, all before we even hit 1500. That's what we would look for in a roadmap. This is telling us you have to have this in your structure. If you don't have this peak, then you don't have that in your structure. IR seems crazy at first, but once we work our way through a couple, it gets really fun and really straightforward. Let's look at another one. All right, so I'm going to help you write your cheat sheet right here. Holy crap, we just hit something huge in this range. That is our OH functional group. That is that. Again, we just learned that we'll always have CH, so that's there. And look at where our CH starts. It's on this side of 3000. So that is all of our single bonds. That's all of those. And then do you notice we don't have anything else until we get lower than this 1500 and we start hitting that fingerprint region. But we've already identified that this formula would be an alcohol. Alcohol is one of our easiest functional groups to identify. And then let's do one more. Okay, so let's take a look at this one. Okay, well, first of all, there's nothing in here. Let's check our CH range. We are on this side, so that's single bonds to CH. Oh, now this one's new, huh? This one is in that 2000 range. It's about 2200. That is our triple bond. Okay, and then you'll notice we've got nothing until we're past that 1500 again. So this is our CHs and our nitrile. This is what a nitrile would look like. So pause this video then. We're going to stop this video in a minute and just compare all three of those. Look at how different that spectrum looked for an alcohol versus a nitrile versus what's called a carbonyl. A C double bond O is a carbonyl. All three of those functional groups, if we can get good at reading what our picture is telling us, all three of those functional groups were quite different. And in fact, I'm envisioning that you've got your functional groups list. Right? And then you've got pKa from our acids and bases. And then you've got IR. Let's put in how you're going to spot that functional group in an IR spectrum. And I would actually like to do an exercise as a class with this. I would like to take our possible functional groups and I would like to identify all of them for functional group. Let's make one massive cheat sheet with this. It's going to be fun. So I'm going to post this document because I want you to have this little guy. Any textbook is going to have one, but I also want you to have the big one. Okay, this one is pretty small and it doesn't give all of our functional groups. This almost gives too much. So it's actually two tables as we scroll. The first one is by frequency. So you can look at by frequency, what's what. And remember, once you get down to like this 1400 to 1000, then, I mean, look at it's getting a little bit intense. We may not need that, but there are 2 functional groups in there. And then it's actually 2 tables. The next one is going to give you by functional group. Oh, how do I spot an alkyl halide? Okay, you don't have CO stretching in an alkyl halide. That's weird. But in an alcohol, you're going to have this big OH group. And in aldehyde, you're going to have your carbonyl. Let me put a little star here because I actually just discovered a mistake there. How are you going to spot an ether right here? So this is by functional group. This table is going to be very handy. All right, and then so that's why this document is so big. You've got tables in here. And a lot of those tables, we can kind of slim that down. That's going to be our job. I hope you didn't get dizzy watching the end of this video as I'm scrolling. Okay, I'm going to post this document, and then we're going to take some time in class to actually read IR together